I'm going to take a breath. So questions about this? Okay. Yeah, so it's, there's some dirty work involved, but, it's mostly, these line integral formulas from vector calc. So let me just remind that in Shear and Levy, okay, for there's an alternate derivation, okay, using D'Alembert, okay? And if that helps you conceptualize it more, then that's good too, okay? Let me make a couple remarks, okay? First of all, as I was kind of saying before, we have a superposition value problems, okay, in that alternate derivation that gives the solution to the inhomogeneous problem, right? That was this idea I was mentioning of sort of taking your D'Alembert solutions and stacking them up where each time is sort of a different initial condition, okay? This is also related to Green's functions, okay, which we won't really get that much into for time-dependent problems. So we're going to mostly talk about Green's functions with respect to the Poisson equation or Laplace's equation later on, okay? But Duhamel's principle, it sort of gets at the region of definition and the sort of standard way of deriving a Green's function for the wave equation, okay? Let me say one more thing, okay? The general solution to the full wave equation, right, that we were talking about before, where you have inhomogeneities in your initial condition, is just going to be given by summing up Duhamel's principle and D'Alembert's solution, okay? So let's say I have now this IVP that should look similar, but now we have this inhomogeneity on the right-hand side. It's essentially just D'Alembert, okay, plus the homogeneous Duhamel principle, okay? And what do I mean by that? It's going to be U is equal to, first of all, the contribution from the forcing. Yeah, that's a C, and then there's a parenthesis there, sorry. T minus S, X plus C times T minus S, F of YS dy ds, plus now, remember our D'Alembert solution. We have the contribution from the initial displacement as well as the initial velocity, okay? And that's it, okay? And remember that the integral of f, I've said this many times already, well, I'll say it again, is over the domain of dependence, okay? Okay. So that's Duhamel's principle. The main thing I want to communicate to you is just, the formula that you have there, the intuition for how to get it, okay? Maybe not necessarily on the fly would I expect you to derive this from scratch, but it could come up on a prelim. But there's two different ways to derive it. Okay, so you should familiarize yourself with the way that we just went through it, and then also the way that it's worked out in Shear and Levy, just to get a good understanding. And so yeah, that's sort of the most general form of the wave equation that we'll look at. So far I've discussed sort of everything in terms of the one-dimensional wave equation. There's a couple of interesting things that happen when you move to higher spatial dimensions, okay? And I just want to highlight those. One point that I want to communicate is what's called the idea of the method of spherical means, and so yeah, what happens when you go to R3 or R2 or something like that? Okay, so so let's do, yeah, okay. So let me start on that now.